This week's Q&A, we're going to be answering the question, how can I quickly check if a large set of data contains any values? And there are some really great ways of doing this using serialized blocks, pointers, and @ constructs. So before we can jump in and do anything, we need to create a function block. And this function block, we're going to call any data. And what this is going to do is allow any data to be passed to it. And I really do mean anything. And then we will check if it contains any value at all. So no matter what the data set is created from, if it contains anything other than 0 anywhere in the data, we will output a true value. So the first thing to do is this only works, or this approach only works, if you go into properties of the function block that we've just created and turn off optimized access. And what this does is optimized access allows TIA Portal to rearrange the interface in a way that optimizes the memory usage, but we don't want that to happen because in order for this to work, we need to know exactly where everything is. So let's go ahead and create our in-out for any data. And it's going to be a variant data type, which means we can accept anything. So what a variant is a pointer to information stored elsewhere. And what's passed with it is its data type. So this block will be able to see what the data type is and what it's made up from, but won't actually be passed the data. It will be passed where the data is located, which means that this can be a small footprint block, but work with very large data. And we're going to need a temporary for storing all of our information that we are working with, and we need it in a particular format. So we're going to need a buffer. So let's create this as a B buffer, which is a buffer of bytes, and it's going to be array 0 to 31, which means we have a 32 byte sized array of bytes. And we're just going to leave it there for now. And what we're going to do in our function block is drop the main function that we're going to make use of, which is a serialize. And now that we have our serialized block placed, let's have a quick look at the interface. So here we have a source variable. So this is our input source. What information are we passing to this serialized block? We have a position, which is used to track the size of the source variable. You'll notice that this is an in-out, so we can't just type anything in here. We have to actually provide a value here, and it's used to tell the system where to start looking in the source variable, and is also updated when certain events happen within the serialized block. We have a return value. This is just a numerical value that gives us a state. So if there's an error in this, it comes out here. If everything's successful, we end up with a 0. And we have our destination array, which is where do we want the information from this serialized function to appear. And you'll notice that if we hover over the input, these are all the things that it can accept. It is pretty much anything. There are a few small things that it can't accept, but it's safe to assume that if you need to pass something, it will accept it. And then we have our destination array. And if I hover over this, again, it says that it can output anything, but there are some restrictions around this. And we will use the buffer, so the B buffer of bytes, and that's what we'll write to. So effectively, what we're doing is we're taking in any value, and we are going to spread that information over our array. So let's go ahead and start populating this. So on our source variable, we're going to pass in any data. This is coming from our outside parent environment where we can pass whatever we need to pass into this function block. And for our destination array, we're going to use our B buffer. So we're choosing none because we want the entire buffer to be used, not just a single element. And this position here, we need to create a new variable for, which we will call POS, and it will be a dint, because if we hover over this, that is what it's expecting, a dint, dword, or time, but we will use dint, and we can just put POS in here. Now, something that we do need to do is make sure that POS is always 0, because we always, every single time this is scanned, we want to make sure that we are starting at the beginning of our data. So we will always move 0 into POS, and that way, by the time we come to the serialized block, we have POS set to 0, and the serialized block will start at the beginning of our any data that we're sending. And then we also need a return or result to store the output of this return value in. And I can just create that as a local temp. So now we're in the position where we have a serialized block that accepts any data. We update our position, so we're always starting at the beginning, and the output is stored in our B buffer. So what we have up here is this array, and what we can do is check if any of these arrays are not 0. Now that's quite cumbersome to do for what is 32 elements, but you can make use of something called the at construct to merge the memory location to another variable. So you can think of it as an alias, especially those that have worked with Rockwell before. So if I insert a row here and I type at and press enter, it will create me a new variable, which I'm going to call LW buffer, and LW for long word. And in here, I'm going to change byte. If I can move the tooltip out of the way, I'm going to change byte to L word and change the size of this to just 3. So both of these variables are 32 bytes long. We have 32 individual bytes that are 1 byte each, and that makes up 32. And then each of these L words are 8 bytes, and we have 4 of them, 0 through to 3, and that makes up 32. And this offset here shows that if I compile this, it should fill in this offset column with how big this function block is. And we can see that both of them are starting at an offset of 0. And if I open this one and open this one and scroll down, we can see that the last element is on 31 and is therefore making up 32 bytes, because this last one starts on 31 and is 1 long. And this one is 0 through to 8, 16, 24, including the size of this last one would make it up to 32. And we can see that the next one starts on 32. So that is both of them the same size, starting at the same memory address. And what that means is that we can write to B buffer, because that's allowed. You'll notice that if I try to write to LW buffer, it does say that it's also allowed, but you'll find that this serialized block will throw an error, because if we look at the help file for this, which we can get to by highlighting and pressing F1, you'll notice that in the table here, where it says destination array, despite the tooltip saying that we could accept anything, it actually says it must be an array of bytes or an array of characters. That's the only thing that the output or the destination array actually accepts. So that's why we have to create an array of bytes, but we don't want to work with bytes. We want to work with the much bigger L word, so we're looking at more information at one time. So now let's have a look at how we can actually check the data. So what we've done is taken anything that we're passing in, and we've got it into B buffer. And because they start at the same memory address, we've therefore also populated the LW buffer. So now what we can do is drop a compare down, change this to is not equal to, and we can have a look at if LW buffer 0 So the first element is not equal to 0. And then we can repeat this for each of the elements. And now we have element 0 checked, 1. Oh, let me change these to 2 and 3. And that will give us our complete check of the LW buffer. All that's left to do now is to send this to an output. So let's create an output, which I will call Q. And that completes our check. So let's get this downloaded into a PLC and in our main OB, a instance of it, and we'll see how it works. Just before we download, I have here an instance, AnyDataDB, and you can see on the front here that it's waiting for me to connect some data. And I've created a SimData data block. And in here, I just have a different mixed array of information or different sizes containing different things. To begin with, we're just going to put in the int value just so we can demonstrate how this works. So let's take a look online. So we're now online to the PLC and we can see that we have a false here and a 0 here. And a quick demonstration, if I were to put a 1 in this value, we can now see that this goes true and this 1 is the one that's here. So 1 here is coming from this data block here. If I change this to a 10, it's still not 0, so we have a true. And if I put it back to 0, it goes false. So let's have a look at what's happening inside this block. So the first thing that you should always check when you set something like this up is that your result is 0, because 0, according to the help, means that everything is okay. And if you ever have any issues, have a look at what this value is. Make sure you set it here, so display format to hexadecimal, and view this in hexadecimal, and it will give you a code that you can look up in the help that will try and help you work out what the problem is. If I go ahead and set this int value to 10 again, we can see that we get an A in this LW buffer element 0, which is not equal to 0, and that therefore turns on this Q. So now let's have a look at the large array, which is this one here. Lots of information in here. It's all Boolean, but it's quite a large array, 1,000 Booleans in here. So let's have a look at what the serialized block is saying inside here. It should be giving us a fault. So we currently have a fault of 32173. Let's change that to hexadecimal, which is 8253. If we look at the help, 8253 says the tag at the parameter destarray does not provide enough memory space for the content of the tag at the source variable. And this is correct because we have a maximum size at the moment of 32 bytes, and we can see that this is much, much larger than 32. The difference between 16 and 142 is much larger than 32. So we would need to increase the size of our buffer, which we could do. We could increase it however large we need it to be. You would have to add more of these elements in, or you could use a bit of structured text to loop it to check if any of them are greater than 0, but you would need to increase the size of your buffer. I just wanted to show what happens if you make that mistake of passing something too big or you keep your buffer too small. It doesn't fault the PLC or anything like that. It will be handled by this serialized block. So let's have a look at the real array, which is longer than just one L word element. So we should see different comparators come on when we set values in here. So if I set something like 145.5 in this one, we can see that the first comparator finds that. And in the third one, if I set a value of 200, we should see the second one come on because we're past the 8-byte threshold at this point. So we're into the next LW buffer. So there are a couple of things to remember with this. The first is really important with the interface. Your buffer must be a temporary. It must be a temporary. And that's because First off, you don't want the size of your buffer to be included in your instance data, because that makes this block really bulky and not very sort of reusable from a memory point of view. If you were doing a lot of these checks, then and you had your buffer in your static, you'd be creating 32 bytes or however large you make your buffer every single time you drop one of these blocks down, which could be inefficient depending on what your use case for this is. And secondly, I'm not sure the at constructor works in static data. I might be wrong on that, but you can give it a go. But I don't recommend using the static anyway. And then the other thing to consider is what this would actually be used for. And this is something that I use regularly. And I use it for checking if a alarm array of booleans, I might have 2000 booleans in an alarm group, to see if any one of those is on. I use it to see if any of my simulation bits are turned on. There's quite a lot of use cases for it once you start thinking about grouping things together and whether or not you need to know if any single item in that group is turned on or has a value assigned to it or something like that. It's very good for queued systems where you have, is anything in the queue right now, or is any system that's part of an array waiting for something. It's very easy to just pick these systems up, pass them through a serialized block and see, is anything active? And if there is something active, then you can then do other methods to determine, well, what is active. But that's a whole different story. But I hope this is helpful, and I hope you've learned some new things from this. And if you have any questions, let me know.